So hello everyone, this is lecture 39 for the mathematical physics. In the last lecture we were discussing about the Cauchy integral theorem, and I was telling you about the simply connected region and the multiply connected region. So what is simply connected region? So it's kind of region in which if you take any circular loop or contour, then it will shrink down a point which will belong to that region only. Okay, means you shrink down this contour, then it will belong to any point. That point will belong to this region, and again this will also. But in multiply connected region, if there is a particular different region R dash where it is non-analytic or it can be any other region, so if you take any loop around it, then when this loop is shrink down to any point of this, then that will belong to different region. So this type of region is called the multiply connected region. Okay, so you can apply the Cauchy integral theorem only to this, where this is the definition: fz is analytic function at all points of a simply connected region in a complex plane, and if C is any closed curve within that region, then integral of this contour to the fz dz will give you 0. Okay, so this was we already discussed. Now let's see some examples of Cauchy integral theorem. So let's take z and dz. Now see this, if there is a power of n is 1 2 3 4 and all, then we know that we get a analytic region, an entire function we get. So let's see where we are getting 0 or not according to the Cauchy integral theorem. So now for this, let's take this contour as a circular loop, because this is our most simple contour, that is circular. So here C is mod z equal to R. So we are taking this example with circular loop in a analytic region. So this denotes the equation of circle, you know about it. Now first we consider for n is not equal to -1, means if you take n equal to -1, then it will be 1 upon z, and for z equal to 0 it will diverge. So that's why we have to take a simply connected region. So that's why we are not considering this n equal to -1, only for the other values. Let's see, for this circular we can represent z as r exponential I theta, because this circular loop can be represented in polar form like this. So from here dz can be written as r exponential I theta will give you I exponential I theta and d theta. So this is simply differentiation. Now let's find this integral. So this zn will give you rn exponential I and theta, and dz will give you this r I exponential I theta d theta. Now from this r will came out and it will give you rn plus 1 here, and you take this iota out, and then exponential I theta and exponential I n theta will give you exponential I n plus 1 theta d theta, and d theta is means the limit will be 0 to 2 pi. Now see, we will integrate this, so it will be e to the power I n plus 1 theta will give you this integration, I n plus 1 in the denominator and this. Now we put the limit. See, this is a constant, so we'll take this out, so I will cancel out, we will get r n plus 1 divided by n plus 1. Now exponential I theta is nothing but cos theta plus I sin theta, so we write it as cos n plus 1 theta plus I sin n plus 1 theta, and theta is from 2 pi to 0, so first 2 pi then 0. So these are the limits. Now see, from seeing this, you know if n equal to -1, then this will be 0, and for that this function will not be defined, means it will diverge. That's why we have taken this n should not be equal to -1. Otherwise you have taken this, then value of this will be 1, and value of this will be 1, and this is minus sign, so this will cancel out, this will be 0, this will be 0, so this whole term will be 0. So if you take any value of n, that will be 0, but n should not be equal to -1. So what you will get, that z and dz will be 0 for n greater than equal to 0. It will be 0 for n minus 2 minus 3 minus 4. For all these values it will be 0, but it won't be defined for n equal to -1 only. See, for n greater than equal to 0, we are getting this 0 because of Cauchy integral theorem. Okay, because for n greater than equal to 0, this will be z1, z2, z3, which will be analytic in all the regions, and if you take any loop, then it will give you 0 because of Cauchy integral theorem. But if you take -2 or -3, then it will be like 1 upon z square, 1 upon z cube. So 1 upon z equal to 0 will not be defined there. That's why that will be not lying in the region of Cauchy integral theorem. So we are getting 0. This is true, but this is not because of Cauchy integral theorem. Here it is because of Cauchy integral theorem. Because here Z and analytic and region R is simply connected for this one. And this is also 0. But for n equal to -1, this is diverse. So we will get something different value, and that will be 2 pi iota. So this is the value we will get. Let's see how we will get this. So for z equal to -1, for n equal to -1, we will get 1 upon z dz from here. So now z equal to r exponential I theta, and dz is this ri exponential I theta d theta. So this will cancel out r exponential I theta. It will remaining only I will be remaining here, and d theta will give theta, and 2 pi minus 0 will give you 2 pi. So 2 pi iota will be integration of n equal to -1 for n equal to -1. So now you have values for every n for the z. So this will be defined like this, means integration of z and dz will be 0 for n is not equal to -1. For n equal to -1, it will be 2 pi iota. Okay, and this is true for any kind of loop. Means we have taken the simplest circle, but it can be square also, it can be rhombus or any other shape, or any polygon, or it can be anything. That will give you same for this fz. Okay, because these are the closed loop as we defined here, they will give you the same values. So let's see one more example, means I am telling you that it will give you same. So let's take a square that will give you same or not. So first let me tell you this one more thing, that in the previous lecture we have taken the circle which have the origin at means center at the origin. But if it is of this kind, z minus z naught, then center will be at z naught. So result will be same. It will be 0 for n is not equal to -1, and 2 pi iota for n equal to -1. So result will remain same. Now here contour is given as z minus z naught equal to r. So this is the equation of circle of this circle. So this result will be same. Now let's see for the square, means we have taken n equal to 2. We can take 3, 4 or 5 also, but they will be very complicated to solve, otherwise we will get the same result. Let's see for n equal to 2. For n equal to 2 we will get z square, and in the Cartesian coordinate z is x plus iota y. So square will give you x square minus y square plus 2 iota xy, and dz will be dx plus iota dy. Now this is the contour given and the coordinates given. So we will consider these 4 segments, first, second, third and fourth. We will separate, means integrate them separately, because these all are the different, means it will be easy, means we can, we can change this complex integral into the real sum of the real integrals. So as I already told you in the previous lecture. So how you can do that? So for the first one, see this y will remain constant, so dy will be 0, and x will be going from -1 by 2 to 1 by 2. So we can use this result. How? For y equal to -1 by 2, for this first segment, this will be then dy equal to 0. Then in the dz, dz will convert to the dx, because dy will be 0. So now this x square and y is constant, so we'll take the value of y as -1 by 2. So you won't consider iota here, it's just -1 by 2 because of the real values. So it will give you x square minus 1 upon 4 plus 1 by 2 will give you iota x, so it will be minus iota x and dx, and x is going from -1 by 2 to 1 by 2. So this will be your limit. Now you can solve this integral very easily. This x square by 2 will give you same values for -1 by 2 and 1 by 2, so this will cancel out, and here x3 by 3, and it will be x by 4. So use the limits and you will get the value -1 upon 6. Then you will take this second segment. Here this x will remain constant, that is 1 by 2, so dx will be 0. So dz will be I dy, and y is going from -1 by 2 to 1 by 2. So it is like this. So x is constant, that is 1 by 2, so 1 upon 4 will be here, -1 y square plus x 1 by 2 will give you iota y, so iota dy. Now solving this and putting the limit, it is 1 upon 2, it is -1 upon 2, so it will give you iota by 6. Now the third segment, here y is constant, and x is going from 1 by 2 to minus 1 by 2, so it's just same, but its limit is changed. So we'll get plus 1 by 6 for third, and same, this is inverse of this, so we'll get the minus iota by 6. Now see, the complete integral will be sum of all these integrals. So 1 minus the sum of all these 4 will give you 0. Okay, so that's how you can prove that this is 0. For n is any value 2, 3, 4 and 5. You can take 3 also here, then expand that according to the cube of a plus b cube, then you will see that you will get 0 again. But for n equal to minus 1, you will get different thing. Means now we have this contour. Let's check for n equal to minus 1 what we will get. So for n equal to minus 1, we have this 1 upon z, that is x plus iota y. Now it will be, let's rationalize it, x minus iota y, x minus iota y will give you this. This is equal to sign x minus iota y divided by x square plus y square. Now I1 will be, in the I1 we have same, this y is not changing, so y is constant, that is minus 1 by 2, and x is going from minus 1 by 2 to 1 by 2. So same, it will be, means dy is 0, so dz dx. So you will get this form, x plus iota 1 by 2. Now see, this fz is this. So for y equal to constant, that is minus 1 by 2. So put minus 1 by 2 here, and x is our variable for the first segment, and dz equal to dx. So y equal to minus 1 by 2 will give you 1 upon 4 here, x square. So you will get this thing for y equal to minus 1 by 2. For second segment, x will be constant, that is 1 by 2. So you'll put 1 by 2 here, and it will remain same other terms. 1 by 2 will give you 1 upon 4 plus y square, and dz will be iota dy, and then 3 for third segment. This will go from 1 by 2 to minus 1 by 2, and y will be constant. So again dz will be dx, and x will be going, y will be from y will be 1 by 2, so you will get minus iota by 2, and 1 upon 4 here for y equal to 1 by 2. So you get all the 4 integrals from this function, and as we did from the last case. Now see how to solve these 4 integrals. See, if there is limit are same and just sign is changed, then we see that the function inside is odd or even. So if you separate this term, x upon this and minus I upon 2 divided by this, so you will get this x upon something will be odd function. Okay, because for minus x and x, it will be fx will be equal to minus fx. So that's why this function will be odd. So this term will be 0, and this term will be remaining. And same for this one, this will be 0, this one will be remaining, this term will be 0, this one will be remaining, and here also this one will be 0 and this one will be remaining. Now see, if you change this limit, means this one will be 0, so only this one is remaining. So if you change the limit minus 1 by 2 to 1 by 2, so it will be 1 upon 2 y square plus 1 upon 4 I dy. So it will be same as I2, 1 upon 2 y square divided by y square plus 1 upon 4 I dy. So these I2 and I4 will be same, I1 and I3 will be same. So this sum of all this integral will convert to this, I equal to I1 plus I2 plus I3 I4. This will give you this iota dx over x square plus 1 upon 4 iota dy over y square plus 1 upon 4. Now it is easy to solve. We remember the formula, 1 upon x square plus a square dx will be 1 upon a tan inverse x upon a. So this is in the form. So this a will be 1 upon 2, a square will be 1 upon 4. So this will give you iota 1 upon a tan inverse x upon a, and limit will be minus 1 by 2 1 by 2. Here also 1 upon a tan inverse x upon a, sorry, y upon a. So whatever result for this, you will get the same result for this. So let's see for the limits. Now see, for 1 upon 2 you will get 1 here, so it will be pi by 4, minus, it will be minus, then minus minus plus pi by 4, so you will get 2 these terms, and 2 iota here. So this will give you pi by 2, so 2 will cancel out, you will get iota pi. Now from here also you will get iota pi, and sum will be 2 pi iota. So total integral is 2 pi iota for this. Now see, this is same for n equal to minus 1 what we are getting for this circle. So that's how we prove that for any kind of contour we will get the same result. For n equal to -1 it will be 2 pi iota, and for other n it will be 0. Okay, as we already proved here, for n equal to 2 you can take n equal to 3 here also, it will give you 0 again. Now there is this one result, very important result. Now we have multiply connected region, means this is region R and inside it we have a different region R dash. Then you will take any contour around it, it will converge to any of this point, and whatever result you will get for that, you will get the same result for any other contour circulating around with this. Means whatever value you are getting for the C1 around this region, you will get the same value for C2, and if any other C3 or C4, any region you have which is surrounding this R dash will give you the same value. The integral value will be same. Let's prove this result. First, what we will do, that we know we can't apply Cauchy integral theorem yet here because it is a multiple connected region. So first, to apply the Cauchy integral theorem, we have to convert this region into a simply connected region. So how can we do that? So first let's take a narrow end from here, and we will made it up to here, to this non-analytic region. So this narrow region will be represented like this, like this. Now we will take a loop which will be lying in this region only. So it will be like this. So this loop is now in this region R, which is a simply connected now. So we know that in the simply connected region the Cauchy integral theorem will be verified. So for this loop A, B, D, E, F, G, A. So for this loop A, B, D, F, G, A, F, Z, D, Z will be 0 according to the Cauchy integral theorem. Now see, this is very narrow. So these D to E integral and G to A integral will be same but opposite in sign. So means first, for this entire loop, let's consider the integrals. We have this A, B, D region, then D to E region, then E, F, G region, and G to A region. So the total integral will be sum of all these. First, for the A, B, D, F, Z, D, Z plus D to E, F, Z, D, Z, E, F, G, F, Z, D, Z, then G to A, F, Z, D, Z. This all will be 0 from here. Now see, this D to E, F, Z, D, Z will be equal to A to G, F, Z, D, Z, because this is a very narrow region and these points are nearly together. Okay, so we consider them equal, almost equal. So now see, A to G is this. If you take G to A, then it will be minus FZ. So G to A will be minus of this. So these will be considered to be 0. Means some of these will be 0. Then only thing is remaining is FZ, DZ, ABD. So if they are almost together, then we can consider that ABDA is a closed loop and this EFGE is a closed loop. Means they are almost together. So we consider this a loop and this a loop. So this FZ, DZ means these are cancelled out. So we'll remaining with FZ, DZ, ABDA will be equal to, this will go to the other side, and minus EFGE. Okay. Now see, ABDA is going in this direction anti-clockwise and AFGE is going in this direction clockwise. So if we convert this to the anti-clockwise, then the minus sign will come out. So this minus sign will cancel this minus and will give you plus. So means now it will be EGFE. So if this minus will cancel out, then ABDA will be equal to EGFE. So you see, the integral value of ABDA will be equal to EGFE. So and both will be equal to the value whatever you are getting for this region. Means this is a R dash region, and whatever value for you are getting for this contour, you are getting the same value for this contour. So this is the result we have proved. We consider this as C1 dash and C2 dash. C1 dash and C2 dash, then they will be equal to each other. So it is not need to be 0. If the value of this is 0, then this must be 0, and if it is non-zero something, then this must be non-zero, and that is the same value you are getting. Okay, so this is the theorem for the multiply connected region. I hope it is clear to you what I'm trying to say. I am just trying to say that if this is a means this is R dash region, means not a simply connected, it's a multiple connected region, then whatever you are getting the value from C1 curve in this region, you will get the same value for C2 or C3 or any contour around it. Okay, you will get the same value, and it definitely not need to be zero, because the Cauchy integral theorem is applied for the simply connected region, and it is not simply connected region. So this is the case. The integral of analytic function over a closed path has a value. The integral of analytic function over a closed path has a value that remains unchanged over all possible continuous deformations of the contour within the region of analyticity. Okay, so it will remain unchanged. It will remain unchanged. So that is the result we are getting. Remember this result, very important. So, and this result, z minus z naught and dz will be 0 for n equal to not equal to -1, and for n equal to -1 it will be 2 pi iota. So these are the both very important results. So remember these results. We will discuss more in the next lecture. Thank you everyone.